Okay. Okay, let's start. Good morning. So we are close to the end. So we will have a lecture this morning and a lecture in the soon after lunch, before the visit. So, do you have any questions? So I know that we are a bit increasing the level of the topics. So probably uh, not all of you are familiar with some of them. So probably the lecture of yesterday was a bit more complicated than the previous two lecture. But so if you have question, please ask now, or feel free to come in our office and ask. Okay. So even if you want to ask questions that are beyond the lecture, the topics of the lecture. Okay. So I tried in this week to give you all the tools that more or less you learn uh, in a couple of years of the PhD. Okay. So, but of course there is much more to tell. So I understand if you are curious about other topics. So while the point up to now was essentially to give you a derivation of of gravitational waves in GR, how these emerge, how these are characterized as a stochastic background. Okay. Uh, we have seen the main sources of that contribute in forming a stochastic background. Okay. Then we have seen both me and Gabriele how qualitatively or graphically, if you want, uh, you can detect a stochastic background, because when you see your signal that is above your noise or your PLS, I would state that this is a qualitative graphical way, if you want, uh, to understand if a signal is detectable. So instead, what I will do today are quantitative, are to give you quantitative tools to understand if a stochastic signal is detectable, first of all. Okay. The significance of the detection, that's the most important things. And finally, the that is not negligible at all. So how well uh, your detectors will measure the signals. Okay. And remember that in the signals there is everything. Okay. When you will have your data stream in your detector, you don't have just a signal. The life would be beautiful without noise. Okay. There is both the signal and the noise. Okay. So and when you perform statistical analysis, or you will process your data. Okay. You need to reconstruct first of all your noise, even more in the stochastic background case, and then do a good job and try to also disentangle the signal from the noise. So in the first lecture this morning, I will tell you how to detect a stochastic gravitational wave background. Okay, so let me already tell you that something that you should remember always. Okay, so it's not possible to detect a stochastic background with a single interferometers, right? Because it's completely confused for the for the for many of the features that I describe. It's almost impossible to measure a stochastic, to detect a stochastic background with a single interferometers. So we should be careful when we define a single interferometers. So yes. Why you mean couple? Because you do. Yes, the reason in that is, yes, the PLS is, let's say, is for, yeah, yes, 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 if you want, yes. Yeah. So uh, let's understand why. Okay, okay. What you need instead to detect a stochastic background, let me already tell you. Okay, so uh, if you want to detect a stochastic background, what you have to do, you have to cross correlate more than one interferometers. Okay, so or channel, because when we speak later about LISA, you will see how we characterize the different interferometers, forming what are called channels. Okay, Gabriele already told you something about this, but the important thing is that you have to take your data stream from two detectors and you have to cross correlate them. So let's qualitatively understand why. Okay, imagine that you have your data stream of your two detectors. Okay, so you have now it will be clear what is this. You have your signal, okay, plus you have the noise of your detector. Okay, in the second detectors you have the signal that is the same, right, because you are measuring the same signal, plus the noise of the detectors. So now imagine that you take D1 and you correlate with itself. Okay, you easily understand that N1 is correlated with itself, is in the same place, so it's hard to disentangle the signal from the noise. Okay, let's instead do this simple exercise. Okay, remember that we have to take uh, correlation function. Okay, so you will have HH. Okay, just graphically, then you have H and 2, then you have H and 1 plus N1 and 2, right? So you just take the 2-point function of this data stream. So with a good approximation, okay, you expect that your signal and the noise are not correlated, right? So these two terms are 0. Then if these two detectors are far apart, or you are able to build a combination of the noise stream that satisfies some properties, okay, so this is at least with the good accuracy also is equal to 0. Okay, so imagine the two LIGO interferometers, or one LIGO and one Virgo, on the two Einstein telescope, or the same Einstein telescope with the combination of the channels, with when it's a triangular one. This is 0. So what you are left with is essentially what we have seen yesterday. Okay, something proportional to hc square. Okay, or if you want, is proportional to omega GW. Okay, this is the simple understanding why you need to cross correlate more than one detectors. Okay, so we will see how the situation is about the noise when we will consider LISA or Einstein telescope in their triangular configuration. Okay, so here remember that it's not one detectors, it's 1, 2, and 3 at least in the simplest case. Okay, or for ET, if you want to know more, there are 3 detectors for the low frequency and 3 detectors for the high frequency. Okay, but you still consider as they would be 3. Okay, so in this case, even if they are collocated, there are some complication about the noise, But what you do, and we will see later, so you call one detector A, one detector E, as you have seen, one detector, okay, is, let's say 1, 2, and 3, okay? And you build this combination here, okay? So this is the simple understanding of why with two detectors we are able to detect a stochastic background. So let's mm, but let's now see what a detector measure, okay? Because the detector does not measure a tensor, of course. What emerge from um, a detectors is a scalar quantity, okay? Is your data stream or your signal, if you want, that is both. I work now in the time domain, and then I will move in the frequency domain, okay? So what emerged from your detector, as I wrote here, is a scalar quantity, okay? So these are ready. Yes, please. We will see. When we arrive at the SNR, I will show you how the SNR scales with the number of detectors. That's the easiest way, okay, to understand. Of course, more detectors you have, it depends also from the geometry, as we will see, how they are orientated. Yes, exactly. -1. Yes. Yes. The the still so do you mean separated detector, right? Of course, not collocated detectors. Okay. But in this case, so I don't think that so the approximation that you do to consider the noise uncorrelated, I will not say that scales so much with the number of the detectors, because you always build 2-point correlation function at the end of the day. So you okay, probably you combine. Uh, let me think. So in the covariance, you should have, yeah, probably you add more noise. Okay, more noise combination in the covariance. So it could be that you, yes, you reduce quite, yes. Yeah, I should think about this. So I never thought, because we usually think about 2-point, okay? So, but we don't add many, you essentially, you inverse weight your noise, okay? So that's the way in which you can count out the SNR scales. So when you add more noise combination, okay? But this is good when they are collocated. I should think about this. Okay, thanks. Thanks for the question. It's very interesting question. Okay, so in your detector, when you will measure it, you will measure a time stream. Okay, so but as I told you up to now, is that my object is a tensor. So and then here we need the missing ingredients. Okay, uh, to 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 extract from your detectors the signal, what you have to do, you have to introduce what is called the detector tensor. Okay, Dij, right? It will be clear soon. That essentially, this is a tensor, is a rank 2 tensor, that essentially describes the geometry of the detector, right? This is telling you if your detector is an L-shaped detectors, is a triangular detectors, is more than that, okay? So essentially what you are doing, you are taking your gravitational waves and you are projecting on your detectors, right? So, and in this way, you can build, if you want, a scalar quantity, okay? That is my signal, okay? Where this is the quantity that we have described up to now, okay? So this will be very important, okay, as we will see. this is essentially yes, one approximation that we can do, and as you now understand, if it is to work in the what is called in the low frequency approximation. Okay. So as you have seen, where this f star is c over 2 pi l, okay, where this is the arm length of the detector, this is the speed of light. Okay, so it's a good assumption that assume that your gravitational waves frequency is much smaller than the characteristic frequency of the detector. Okay. So you have already seen from the exercise that as long as you are in the low frequency approximation, okay, your detector tensor, or what we will see is the response function or the overlap function, is constant, right? So this is a good simplification because you don't need to take into account all the oscillatory behavior. Of course, this is, as it's called here, is an approximation. When you want to do the full analysis, you have to take into account the full detector tensor, the full response, and also the oscillation. Even if, okay, this is a bit long to explain. What a lot of signal on the stochastic backgrounds that you acquire is in the low frequency part of the detectors, okay, and it will be clear when we will write the SNR, okay. So in the low frequency approximation, okay, so this detector tensor has a very simple form, okay. This is 1/2 y j minus y Vj, okay. And where this u and v are unit vector along the arm of the detector, okay. So essentially you are telling to your gravitational waves to project on a L-shaped detectors or something different, okay. So let me switch here. Then this is the first, this is the detector tensor, yes. This is the first quantity that is important to detect a stochastic background. Then you can introduce another useful quantity, fa of n, direction of function of the direction, okay, dij aej, sorry, of a, okay, when, okay, I call n, I call a, these are the plus and cross polarization. So I switch from P to A because it's okay. This is the gravitational waves direction. Okay, yes, and this quantity is the detector angular pattern function. So sometimes you will find a different nomenclature, okay, uh, but okay, the meaning, the physical meaning is the same, okay. Yes, it is important because this quantity, right? So essentially comes from this, from the to project the tensorial quantity of the gravitational waves. So now that you have this, so you can write your data stream, right? Because you have remember. So I do a slight modification, okay, to the gravitational wave signal now, because we work in as we will see, uh, we work in time domain, okay, but we have our signal, the Fourier transform of our signal, okay. This is Yes, here is A because these are two, right? This one is for plus and one is for cross. Because essentially these are the gravitational waves wants to know where it must project, right? So it's different if you project on an L-shaped detector or with a triangular shape or with something else, right? So for the tensorial nature of the gravitational waves, right? So let me write my gravitational waves, okay, as A. This is the integral between minus infinity and infinity, dn, okay, epsilon ij a of n, hp ha of f and direction n, e to the I to p f t minus n dot x, okay. So now this is my eigenmodes, my mode function of the gravitational waves is a bit different from when we see it from the in the primordial case, but it's very easy to make the two notation consistent, okay? So in the notes that I will give you, there is also these small details. So then the next step is to build my h of t, okay? That is the contraction between dij and hij. So what you will have is that okay. Let's now see what is this for an L-shaped detectors, just to give you an idea. So let's we compute the pattern function for an L-shaped detectors, okay? So you can do also the exercise for a, sorry, don't go directly here. You can go also for something like this, where this is 60 degrees, okay? So what you do, you define your orthonormal basis, okay? This is 1, 0, 0, T, V is okay. And this is Z equal, okay? So, and you assume essentially that you have U and V, okay? So in this way, if you compute D, it will give you something simple, okay? Okay. So of course, here we have been very specific. So you have to perform two rotation to be in the most generic case, because you don't want to have some fake dependence on the direction. Okay. So you perform the first rotation. Okay, that is cosine of theta, cosine of phi, cosine of theta, sine of phi. Okay. And then if you want to be even more general, you have to perform another rotation, okay, around the direction of the gravitational waves, okay. So if you perform these two set of rotation, okay, you go in this general frame, Okay, now I call the direction of the gravitational waves omega. Okay, so this is the cosine phi sine psi 0 minus. Okay, so this means that now your new unit vector will be prime cosine psi plus v prime sine psi. This is n. Okay, and this will be okay. It's this way. Okay, so omega. So now that you have this very general frame, okay, you have to compute your polarization tensor. Okay, whether I call it a ij plus, this is mi mj minus ni nj. Okay, this is cross mi nj minus ni nj and I mj. Okay, so and now you have everything to compute your pattern function. Okay, so if you do a bit of algebra, you will have your pattern function for the plus mode. Okay, that will be dij epsilon ij plus. Okay, so you do this and you will find that this is equal 1/2 1 plus cosine square of theta cosine of 2 phi cosine of 2 psi minus cosine of theta sine of 2 phi times sine of 2 psi. Okay, this is the f plus and this is the f cross. Okay, and this is similar to this. There is a minus 1/2 here. This is the same. Here is the same, and this is sine of 2 psi. And here you have, instead of sine of 2 psi, you have cosine of 2 psi. Okay. So, and this, if you look, uh, if you look in the literature, will give you the angular dependence of your, if you want, of your detectors in 3D. Okay, you have sometimes seen plot like this. Okay, this is okay. I didn't have a picture here. So this is telling you the angular sensitivity, if you want, of your detectors, assuming a specific direction for your gravitational wave. And you will also see that some of these direction, for instance, are blind to gravitational waves arriving from some specific direction. Okay, that okay depends from the geometry of the detectors, and this is different from the plus and from the cross polarization. Okay, this is giving you an idea of uh, of the angular sensitivity. So what is the complication when we are not in the low frequency regime? Okay, so when you are not in the low frequency regime, you have to assume that that there is a transfer function. Okay, it's not a very hard complication, but it's some things that you have to take into account. Okay, so and in that case, so essentially So your detector tensor, okay, will be something like this t times what I wrote before, y uj minus y uj, okay, where this transfer function, so that you can build, okay, uh, yes, is quite long calculation. Okay, this is t. This is, for instance, so I don't derive, but this is a1 times f. For instance, in the case of Lisa, this is this. I substitute a1 with it will be clear soon. F minus f star 3 plus omega dot a1. So this is keeping information about the path that your photons does in your detector in the first approximation. Okay, so this means that now your pattern function, okay, will be something like dij, that now is a function of the path of your photons. Okay, and always you have the projection on your gravitational waves. Okay, where now within the d there is also the transfer function. Okay, so but what I showed before is that is only for one detectors. Okay, so but at the beginning I told you that to detect a stochastic background, okay, you need to correlate two detectors. And what we will do, we will extend the previous calculation to the two-point correlation, okay, and to the computation of the estimator to detect a stochastic background. That is the signal, the signal to noise ratio, okay. So let's do this computation. So if I have time at the end, I want to come back to the transfer function, okay. So let's do two detector correlation, okay, because this is the, let's say, the main tool to detect a stochastic background. So we still assume that we are in the low frequency, okay, low frequency approximation, okay. So now I have two detectors, so I have to keep track, if you want, of which detector I have. This J, assume that you want to do a two detector correlation. J is 1 and 2, okay. So you have Sj of t, that is my signal in one detectors, then we will see, and then you have Nj of t, okay, the noise in the two detectors, right? So now I write my Hij, H of t, Hj, okay, the signal of t, and Xj, okay, because this now relates to where your detector is, okay, this is the detector position. And now we have the sum over A, df between minus infinity and plus infinities, okay, you have d to n is the extension of what I wrote before, okay, to the case in which we have two detectors of n, h a of f, and then yes, this is a nice question. So it's a common convention to do from minus infinity and infinity. Then it's easy to switch from 0 to infinity, and you have to add the factor here to take into account that you just consider positive frequency. But this is the usual convention that we use. Also because remember that these emerge from a Fourier transform. Okay. So now keep track of the index j that identify your detectors. Okay. So j is the detector location. Xj is the detector location. Okay. So we know what are the f. Okay. So since we want to correlate two detectors, let's now define a quantity y, okay, that is essentially our signal. This will be the integral between minus the observation times divided by 2 over t. Then you have another integral of minus t half and t half over dt prime. Then you have s1 of t, s2 of t prime. Remember that of some function that is q minus q of t minus t prime. Okay. So this is the signal in the first detectors, this is the signal in the second detectors, and this is a very important quantity that is called filter function. Okay. This is t is the observation time. So why I introduce this filter quantity, this filter function? So the reason is when we will compute the SNR, we will see that whatever signal you want to observe, so considering the signal that you are looking for, so there is a filter function that maximizes my SNR, okay? So the main target of the analysis, considering the stochastic background that you are observing, you have to find the proper filter function that maximizes your signal, okay? Your SNR. And we will find it in the case in which we study here, that is a simple power law, okay, isotropic. So, but it's easy to extend also to other kind of features of the stochastic background. Questions? Okay. So, since it's easier to work in frequency domain, and everything that I have shown to you was in essentially in frequency domain or in K. So let's switch in frequency domain. So I typically use this convention for the Fourier transform. Okay, this is g tilde of f e to the pi to ft. Okay, so this is the way in which you split from time to frequency domain. So now I have my hj tilde of f and xj. Okay, that is a times I don't know why I start writing a here, because on my notes I have b that was consistent with the old one, but anyway, let's continue with a. Okay, I just simply Fourier transform my data stream. Okay, so if you do now, you have to of course go also in the 2-point function and perform and insert this Fourier transform. So if you do it, what you get is that the two-point function two-point function, okay? So I still have not taken the average. I will take it soon, okay? The y is the integral between minus infinities and plus infinities, the f prime, the f double prime, delta of t of f minus f second, delta t of f prime minus f second, s1 star of f, s2 of f prime, times q of f second. Okay, let me clarify. Can you read it? Okay, so let me clarify what enters here. Okay, so I have introduced some things that you have probably never seen. Okay, that is delta on a finite time. Okay, t, because remember that I'm observing for some finite time. Okay, unfortunately I cannot observe forever. Okay, so this is minus 2/2, and this is just a definition of e to the 2 pi t f, that if you want, this is n of pi f t over pi f. Okay, this is just a definition. Okay, so but this kind of finite delta has a very nice properties, because in the limit in which the product of the frequency times the time goes to infinity, okay, this becomes equivalent to a Dirac delta. Okay, so in the limit in which this goes to infinity, okay, delta t of f goes to a Dirac delta. Okay, so let's see if we can use this approximation, because it's not still clear. Okay, so imagine ground-based detectors. It works also for other detectors, for space-based detectors, but typically a data stream, an observation times can be of order 1000 seconds, okay, and you have frequency, you say, let's say 10 hertz, okay. So this means that your f time t is of order 10 to the 4, okay. That I think that is a reasonable approximation to substitute delta t with a Dirac delta, because this simplifies a lot our life. So, and if you do this replacement, okay, you simply get that your y is equal to, is almost equal to the integral from minus infinity and plus infinity. Is a very simple form. Of course, I integrate over the deltas, okay? And this now is, of course, is the Fourier transform of the filter function. So I didn't put the tilde on top, but when you see in F, it's the frequency, is the Fourier transform of that ones. So, but now we still have to do the average, because remember that to define a stochastic background, we need to do this so-called ensemble average that we typically replace. Okay, let me do here. We typically replace with the time average. Okay, so again, you assume that your noise of the detectors are uncorrelated, right? And you take your ensemble average, right, of your signal, that essentially is this ensemble average here, right? So what I did my ensemble average, that I substitute with the time average, right? Is the equivalent for the ergodic theorem, okay? And I assume that the noise are uncorrelated, right? So this means that here, so I'm left with when I have S1 star of F, S2 of F. So the only things that remains is one H1 of F, H2 of F, right? So all the other terms are zero, because here I should have a mixed term, Hn, two mixed terms, let's say, that are zero, and plus N1 and 2 star that is zero as well, because I assume that the noise are uncorrelated, okay? So then I can replace this in my 2-point function, and you already know what happens, okay? So at the end, my signal, okay, the signal that is the 2-point function, okay, averaged, will be equal to the integral between minus infinity and plus infinity of h1 star of f. And now this is very nice because it connects with what we have done up to now, okay? You see what happened, okay? There is an integral over df, okay? You start recognizing what we have taken from the early universe or from the astrophysical sources, okay? So you start looking something, you start seeing something familiar. So now you have to plug in, so I pass from, I fix J1, 1 and 2, so these are the two detectors, okay? So then you plug in your signal, okay? You have df, you have the sum over A and A plus over 2 polarization, dn, okay? So I am quite general here. I can also, okay, let's put it to be as complete as possible. So remember that we still have our filter function, okay? So I just took, I just replace these here, okay? And remember that we still have the average, okay? So now if you remember the lecture the last lectures, so the 2-point function, my 2-point function, okay, So this is my 2-point function of my gravitational waves, okay? So I told you the properties that characterize these gravitational waves, that is the power spectrum. So what typically is done is to write essentially in a slightly different way. Instead of using the characteristic strain, uh, I use the quantity SH that we have introduced yesterday, right? The reason is clear, is related to what I told you at the beginning, because the easiest way, let's say, to quantify the SNR, okay, is in terms of this, okay? But is you can do also in terms of H, the characteristic strain square. So, and the properties that you have are always the same. The isotropy, if you want, the 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 stationarities, okay, the unpolarized, okay, and I just write it in terms of 1/2, okay, put one, yes, SH of A, okay, of F, okay. This is the same of H. As we will see later, this can be also written in terms of omega, okay, yes. The psi, yes, because remember that I put in the most general case, okay, where I introduce also this rotation about around the direction of the gravitational wave. So that's the most general case. You don't lose so much information, but it's important because for the astrophysical case, also for some cosmological, but for the astrophysical case, that terms matter quite a lot. Mhm. Okay, of course, depends from the distance between the two. There are some level of correlation, even at very long distance between the detectors. In principle, so you assume that when you perform the analysis, this very long correlation, you are able to model. Okay, so if you are able to model this long correlation, in principle, you can subtract from your data stream. But even so, they are very weak. So we typically control quite well, but still there is a small level of very small level of correlation. Yes. Yes. Okay. So this is my other questions. No? Okay, then this is the first property that I use. The second properties that I use is I use again my finite delta, okay, that is the integral, okay, and then I use a third properties of the delta that you can check, that the delta of 0 is equal to t, okay, it's observation time. So if you plug uh, all of these there, okay, what you get is the following. You perform all the integration, okay, then you have fi a of n okay, where I have introduced delta x, that is the distance between xi and xj detectors, okay, and you have again your filter function that we have still to find, okay. So let me write in a more compact way, and it's nice because this is for gravitational waves, but is valid for every kind of detectors and signal that you have, even outside the frequent, in other bands, okay. This is a standard calculation that you do for the SNR, okay. So this means that this my signal is equal to the integral between minus infinity and infinity of sh of a times, let me introduce a new quantity f times my filter function, okay. This is a very beautiful equations formula, because let's read it, okay. So you have that your signal, as you would expect, okay, is proportional to the observation time. So longer you observe, more signal you get, okay, as you would expect. So it has information about your source, the stochastic gravitational wave background source, okay. This is only related to your source. That's very nice because you take your source and you project on your geometry of your detector, right? And then you still have to struggle a bit to find this filter function that maximize your signal, okay? That is very simple, if you want, physical interpretation of this formula, okay? Easy even to imagine before the we do all the computation, okay. So if you want, so as I was telling you before, so your signal can be also written uh, in terms of omega. I don't remember. Ah, yes, 4 pi square here. Sum over a, the integral between minus infinity and plus infinity, df. Ah, yes, that's the reason why I wrote here. Okay, it's the same as before. So let me write just the final formula in terms of omega. Yes. 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 Ah, okay. Sorry, I didn't specify what is gamma. This gamma is essentially. Let me write it. So I didn't have here. Yes. Yes. Essentially, this gamma here. It's in general defined. If you look at here, okay. When I say geometry, I mean all this part here, right? So all the integration over the angular direction, the psi, the n, this contribution, and the overlap function. Okay, sorry, I skipped the definition. This is 0 to psi over the psi over 2 psi to pi. Thanks for the question, because there is an important comment to make here. Okay. So why this is times? Okay. So why this is very important? Because this is the so-called overlap function. Okay. Let me tell you some. Let me see if I first of all if I define overlap reduction function. Okay. And this of course is summed over A. Okay. So why this is very important? Okay, because I have defined later. This is very important because it's essentially, as I was saying before, it all the description of the geometry of your detectors. Okay, let's see why. So you understood this part, okay? That is the pattern function, okay? So you have a projector of the direction of your gravitational waves on your detector geometry, okay? There is an important factor here, okay, that keeps into account how far your detector are, okay? This is delta x is the distance between the detectors, okay? This function is not, this keeps into account where on the earth you will plug your detector. This is the distance between these two detectors. And this is very important, this quantity, because it changes your response of your detector, okay? And then, of course, you integrate over the sky variables, okay? Yes, this is a very important quantities, this gamma. This is the most hard task to compute when you have a new gravitational waves detector. So if you have defined this and you want to write your signal in terms of omega instead of s, what you will have so this means that in the exercise of yesterday, you take your favorite models, that can be an astrophysical model, right? An astrophysical background. You project on the overlap function, you multiply for the overlap function, okay? And still at the moment you cannot compute the filter function. You don't know still the filter function. And you keep into account if you work in omega units of this factor, okay? Other questions so far? So, yes. It's exactly the same as before in terms of omega instead of in terms of s. No, the integration in the sky variables is here. Yeah, yeah. What you give here usually is the integrated one, the isotropic one. Okay, you don't consider still integration there. So what you typically do, since this guy contains all the information of your detectors, the geometry of your detectors, so you this is not normalized, okay? You normalize them, okay? And you define typically what is called gamma, that is more common to find in the literature, okay? Normalized overlap function, that is essentially gamma ij of f times what we call here fij. Okay, this should be okay. Let's write in this way. It's clear what this means, so don't be scared. These are just to identify the detectors, where this fij below is the same of this, is the same of gamma ij, but to that with considering two detectors collocated and aligned. Okay, this is just a normalization that is telling you that if you have two detectors far apart, whatever they are oriented, so if you compute the overlap function, okay, for this, it should give you 1 when you collocate and you you aligned. Okay, so for a ground-based detectors like LIGO, for the two LIGO, okay, this is 2/5. Okay, this, if you want, okay, is the value of the response of the overlap at low frequency that you have to plug when you estimate your signal, for instance. Okay, this is only the low frequency part. So remember that yesterday, when you see the response of Lisa, you have seen something like 9/20. Then here you have some numbers plus numbers times f over f star. Okay, to some power here. This is the also this is the low frequency approximation, right? So there is no transfer function inside. Here there is no transfer function inside. Okay. So if you do everything, so at the end, what you get that your normalized overlap function is gamma ij is phi over 2 d to n over 4 pi. I have integrated over psi. Okay. Then you have the sum over the two polarization of fia of n, fja of n. Okay, this is the normalized overlap function or response function if you want. So, and if you put everything inside your signal, so in terms of omega, you will have something like this. So it's the same things to work in omega or in S. It's just that I give you, for completeness, all of them. Okay, so I have again my signal model times the geometry of the detectors times the filter function. Now it comes a beautiful part, because as I told you before, so the estimator is the signal to noise ratio. Okay, so we still need to compute the noise. Okay, let's see how to evaluate the noise. Okay, to arrive at the definition of this SNR. So we consider the case in which we are noise dominated. Okay, so there is no signal at all. Okay, so the noise will be mainly given by the variance of my signal, right? That's the standard way. So my noise will be just y square minus y square, okay, in the noise dominated case. Okay, this is the standard definition of noise. So if you like two-point correlation function, and if you do the you compute your variance, essentially this is the variance of the signal. Okay, so you will get something like df prime, and here you will have right? I have just written the usual definition, where now I have the 4-point function of the noise times the product of this 2-point function of this square. Okay, so of course, so since we have assumed that the noise is not correlated, so I have assumed that n1 and 2 is 0. Okay, so the second part, the second line will disappear. Okay, so then what you do, you still have to solve the first 4-point function. Okay, you assume that your noise is stationary. Okay, and you define what people that works in the gravitational waves community, okay, what is called the one-side noise spectral density, or PSD. Okay, or if you want, noise power spectrum. Okay, one side PSD. Okay, that I call it Pn, and this delta of f prime is a translation of the stationarity of the noise. Okay, so this is the guy that Gabriella gave you yesterday. Okay, so remember that this is in some units. Okay, this is yes, this is the noise is in hertz to minus 1. It's written in this way. So this is hertz to minus 1. So this must be hertz to minus 1. Okay, this is the way in which you can go around, as usual in physics, is considering dimensional analysis. Okay, so this is the power spectral density, as in the case of also resolved sources. Okay, so since the noise is real, okay, so this is one properties. N star of f is equal to n of minus f. This means that Pn of f is equal to Pn of minus f. Okay, so if you now take the first 4-point function and you take the combination using the Wick theorem, if you want, you are left with n1 star n1 of f of times n1 of f prime, and then 2 times n2. Okay, so I can skip this step. So at the end, what you will get is that your noise square, the variance there, is equal to t over 4, the integral again between minus infinity and infinity, the same filter function that I had before. Okay, then you have p of n1 of f, p of n2 of f. Okay, where again I have used the property of the delta. Okay, so there are a couple of important things that I like to stress that give you just a naive. Okay, I could not cancel. So if you look, if you compare the signal and the noise, okay, you realize that the signals was scaling with time, with observation time. Okay, so while the noise is scaling with the square root of the observation time, right? So so now I can define what I was hoping to to compute, that is the signal to noise ratio, my estimator, okay? It is essentially given by the ratio of the two quantities that we have computed. So you have t over t to the 1/2, so you have square root of t times minus infinity and plus infinity, okay, df of sh of f gamma. So I still write sometimes in terms of gamma and sometimes in terms of, okay, I can even, okay, let me write gamma here, then we will plug the other one, q of f over df right? So my signal over the noise. So the important things to realize here are two. One is this tau to the 1/2 dependence, okay? So the SNR scales with the square root of time, okay? The other thing is that I still have to define my best filter to maximize the signal to noise ratio. Okay. And if you want, you can rewrite this in terms of omega. So let's now see what is the trick that you can use to find your filter function, because this is the final step. So we need the filter to find the filter Q that maximize how is it? Okay. So to find this filter, you introduce what is called the positive definite scalar product. Okay. Between two functions. Okay. So this is exactly the same as is done with the match filtering, okay, with the waveform. But so you introduce your positive defined scalar product that is defined as a star of f times b of f times p n square of f. So I already, okay, you can define in the general way. So in this way, as soon as you have defined this positive definite, sometimes you find also these thing here. So if you have these, so now you can write your SNR, okay, as square root of t q times gamma ij of s over pn square over qf, okay, to the 1/2. So you can write your SNR using this, if you look at my definition above, okay. So, and this is essentially is a linear algebra problem, okay. these are two vectors in linear algebra, okay? So if you are looking for the direction, if you want, that maximize the scalar product, okay, this scalar product, you will find that the Q function that maximize my scalar product is a constant times a function of gamma ij of s h of f over p n square, okay? So this is the filter that maximize my SNR, right? Of course, the filter must know about your detectors, the filter knows about the signal, and the filter knows also about the noise of the signal, right? So this is something that you could expect. Here, I have defined what is this Pn, okay? Square is just to compactify the notation of this Pn2 of f to the 1 half, okay? So it's very important to stress that the signal the filter depend on the signal that you are observing, okay? So the filter must know if you are looking for a cosmological background, you are looking for an astrophysical background, the model, the underlying model. So in this way, so we are close to the SNR, the optimal SNR, okay? So in this way, the optimal signal to noise will be something like this. Okay, and okay, explicitly, so if you write your scalar product, this will be the square root of time times the integral between minus infinity and infinity, okay, df over gamma ij square of f s h square of f times p n 1 of f p n 2 of f, okay? So final step, okay, I write it in terms of omega, so you have everything, 3h naught over 10 pi square root, there should be a square here, right? Okay. Yes. So check that I introduce all the normalization, right? Okay, it should be. So let's comment a bit on this because you have everything to compute the significance of the signal that, can you read it? So, okay. So let's comment a bit on it. Okay. So again, I want to stress this because more time you observe, more signal to noise you get. This not means that for sure everything will be better, okay? So the other things that I want to tell you, the interpretation again is geometry times your model, okay, times the noise of your two detectors that you are cross-correlating, okay? So one thing that I want to highlight is this, because it's related to some things that I told you before. So when you write in terms of omega, okay, but even in the other case, so if you do the right things, so you see that this goes as 1 over f to the 6. So this means that in the low frequency part, okay, you acquire, you sum a lot of signals, okay? So that's the reason why at the beginning I was telling this. This is also one of the reasons why we try to push in the low frequency, not the only one, of course, but is one of the reasons for which, for the stochastic background, pushing the low frequency is very nice, okay? Final thing, okay? So you can also define your Sn, okay? I think that Gabriele yesterday did it, okay, as Pn over gamma, or small gamma, or big gamma, okay. So if you redefine this, okay, this is essentially you essentially redefine a quantity that has inside the noise of the detectors, the ones that you see yesterday for Lisa, N, A, and so on, over your response. This is essentially the formula that Gabriele wrote yesterday in the exercise, okay? So in this way, so your SNR is simply proportional to the square root of t of S of h over Sn square, right? And essentially, of course, integrated over the frequency. So you now understand what means comparing the noise of your detectors, okay? This is the noise of your detector with essentially the signal. I have consider that I have used that definition over the signal, okay? So naively, I would expect that whenever you compute an SNR, you have the ratio of your signal over the noise, okay, times some things that takes into account how long you observe, and consider that, of course, when you do this computation, when you have to do this computation for your detectors, here the integration band is f min and f max. Of course, you don't integrate between minus infinity and infinity, where these f, okay, are for instance, in the case of Lisa, this is 10 to minus 5 and 0.1, okay, where you have quite control of all the noise, okay. In the case of LIGO, you have this between 10 hertz, okay, and I don't know, 10 to the 2, 3, okay. Okay, so you do this integral and you compute the SNR. Of course, so remember that the SNR is a way to quantify the significance of your detection, okay? So before going in the accuracy of your detection, you are quantifying the significance of your detection. So just to, before to conclude, of course, so so you have seen yesterday that the SNR is the starting point to compute the PLS, because you need to set an SNR threshold, okay? That depends, as you can understand, from many reasons, okay? From the signal that you want to observe, from the detectors that you are considering, and also from, if you want, the noise of your detector and the number of the detectors. So the typical SNR that you have for an array of detectors, it should scales in this way, right? If I remember well. Yes. So this means that, of course, so more detectors you have, okay, so you can increase your SNR. The point that I want to stress, okay, here is the following. So when you look for a background, okay, so claim a detection of a background with SNR1, as you can imagine, with all the approximation that we have done, Okay, the noise is completely uncorrelated. There is no correlation between noise and signal at all. Okay, we have assumed that the noise is completely stationary, and so on and so forth. This is something a bit risky. Okay, so we typically for Lisa, so when we derived the first time the PLS, okay, it was invented much time than when we recomputed. So we typically assume that a stochastic background can be claimed as detected with an SNR over the rate. Of course, so if you have the reasonable signal that we have seen yesterday, so you cannot expect. So if you want, let's look at this figure. Okay, so in terms of omega, for Lisa, the PLS or the is around 10 to minus 12. Okay. So if you have a signal that is here, okay, this is what I was telling you yesterday, and you have computed your PLS assuming SNR threshold 8, you expect that the signal that is tangent to the PLS will have SNR 8, right? Because you have defined, okay, considering the observation time, but you have defined this in this way, okay? Of course, when you look some plot, if you want, you can have already an understanding. So if your PLS is here and your signal is here you have 2 orders of magnitude, for instance, of difference between your noise and your signal. You can have already an estimation of the SNR of your signal, more or less, a rough estimation of the SNR of your signal. This does not mean, okay, even if the SNR is low, okay, this does not mean that the signal cannot be seen at all. Okay, this just means that, as we will see in the second part, so the detection of your signal will most probably come with large error bars. Okay, so and you still can be able, to some level, okay, it depends, to reconstruct your signal. Okay, doesn't mean that if it is completely um, if it is slightly below, you cannot see, because it depends how well you reconstruct your noise. Okay, so this is something that we are doing. I think that this is a part of the pipeline for Lisa, for the stochastic background. This is what we are developing. Okay, is this SGW binner code. Okay, this is a official pipeline for Lisa for the stochastic background, where you do the exercise is the following. Okay, there will be something that will be even more clear in the afternoon. Okay, so you take your PLS. Okay, you assume that your signal, for instance, is a signal like that. Okay, is a completely general power law. Okay, let's do it with something realistic. Okay, so as I mentioned at the beginning, so there are two guaranteed astrophysical background in the Lisa band. One are the galactic binaries that have a shape like that. Other one are the stellar origin black holes. Okay, and these are galactic binaries. So remember that when you will switch on your detectors, you will have your astrophysical sources resolved. You will have these foregrounds. For us, is a foregrounds, and then eventually you can have your I don't know. For instance, your scalar induced stochastic background. Okay, so you will have a mess. So the first thing that you will do, you will try what we thought. Of course, there are also other people that think differently. Is let's split all this frequency band, okay, in many bins. Okay, let's assume that my signal in each bins, okay, is a power law. Okay, let's compute the PLS bin by bin. Okay, And let's compute the likelihood, something that we will see in the afternoon. Let's minimize the likelihood, and let's find the best possible signal that can reconstruct my frequency shape. Okay, so in the sense that so in each frequency shape, in each frequency bin, I can have an understanding of, if you want, if you write your wave or your spectral energy density as an amplitude and a spectral tilt, okay? In each bin, okay, you will have a best fit value, okay, for your amplitude and the best fit, let's write like this, for your tilt, okay? So you will have bin by bin your reconstructed signal, okay? Of course, the starting point for doing this is computing the SNR, because so the accuracy of the reconstruction, of course, scales with the SNR, okay? More or less, we will see in the afternoon better. As long as you are able to reconstruct this signal, okay, better you reconstruct, better you subtract for your data from your data streams. So remember that these two components, the galactic, as I was saying before, the galactic and the stellar origin black holes, so these are two foregrounds. So whenever we will switch on LISA, this will be there. So we have to find the way to characterize these and subtract them from the data. Only when you have done this, because these guys here, if you want, enters here. These are noise contribution, right? So these are foregrounds. That's the reason why we call them foregrounds. So this means that they tend to kill your SNR, okay, of your signal that you are looking for. So here I just accounted for the variance of my signal. Of course, here, so you have to include also the instrumental, so this kind of foregrounds, okay? So this tells you why the SNR is crucial, is a crucial estimator for the stochastic background, because it allows you to set, to compute both this threshold, okay, that you need to know. It tells you, it has information about the detector geometry, the noise and so on and so forth, and allows you, for instance, to, this is one of the tools. Another tool that we are also working at the national level, okay, with the national coordination, is the following. Instead of considering these three signals independently, so let's consider the data stream that is the sum of everything, okay? The foregrounds, the signal, the resolved sources, plus everything that you can have. And instead of doing the reconstruction of a single step one by one, if you want single source by source reconstruction, we do what is called the global fit, okay? Okay, we fit everything together. So this means that whenever you will have your data stream, your data stream will be characterized by something like, your signal will be characterized by something like, depends on the mixture that we want to do, something like 20, 30, 40 parameters, okay? That you have to multiply by the number of sources that you see, measure, and you have reconstructed, and you have to reconstruct all to fit all these parameters at the same time, okay? So in the afternoon, instead of showing you these difficult tools, so I will show you, I will try to tell you the easiest way to estimate, for instance, for a signal like a power law, the accuracy on which you can measure, for instance, assuming that you have a stochastic background, a power law, how well you can measure the tilt of this power law, okay, and the amplitude of this power law, and what is the error, if you want, that you have on the reconstruction using the Fisher matrix. And okay, I think that I stop here, and if you have question, so I don't know if it was a bit, the calculation are not so complicated, right? The concept probably could be a bit new, but if you have question, please. The idea of the small pieces, instead of doing a full fit of the full shape, you split the shape in many sub. The gain is that there are two sides of the gain. One is that if you do this job right, the noise reconstruction in sub bins allows you to increase the accuracy on your noise modeling. The second one is that you are able to keep into account reconstruction also of complicated signal that without a binning, so it's hard to the stellar origin black holes. Yeah, exactly. So you are able to keep some features that without this binning is they are hard to catch. Yep, exactly. Other questions? No? Okay.